Hey guys, here we go with this unit on solutions. A solution is a homogeneous mixture of one or more solutes dissolved in a solvent. Remember, homogeneous means evenly mixed, so these are just mixtures of something dissolved, usually in water. Here are some examples. Coffee beans are dissolved in water, the extract from it. Sodas are a mixture of sugar and CO2 and water. And in chemistry, we use lots of different things for solutions. Most of our reactions that we've been studying are aqueous, remember, in water, and this is why solutions are important. There are two parts of a solution: the solute, which is the substance that dissolves. It's the minor component in a solution. The solvent, substance that does the dissolving, it's the major component in a solution. So if you were to dissolve some sugar in some water, the sugar is the solute and the water is the solvent. Here's a little example at the bottom there. If you dissolve 1 tablespoon of sugar in 12 ounces of coffee, the sugar is the solute, less sugar than you do water. And the coffee is the solvent because it is the major component of the solution. So here are some factors that affect the rate, how fast a solute dissolves in a solvent. These are all pretty much common sense. What do you do when you want to dissolve your sugar in some coffee? You stir it. Stirring makes it dissolve faster. Another factor is the temperature of your solvent. Which do you think sugar would dissolve more quickly in, an iced coffee or a hot coffee? I bet you'd guess it was the hot coffee. Typically, the hotter the solvent, the faster the solute will dissolve in it. Also, the size of the particles are a factor. If you have smaller particles, like granular sugar, it will dissolve much faster than, say, cubed sugar. Again, all very much common sense. Here's a key term in this unit. It's the solubility. The solubility of a substance is the amount of solute that dissolves in a given quantity of solvent at some temperature. So here's a couple of examples down here. Sugar is very highly soluble. You can put 200 grams of sugar in about 100 grams of water. That's a lot. Sugar is very soluble. If you compare it to salt, you can only get about 35 grams of salt in 100 grams of water. If you try to put more in, say you try to put 70 grams of salt in 100 grams of water, about 35 grams of that are not going to dissolve. You're going to have about half of it sitting at the bottom of your glass undissolved. Here's a bunch of different key terms that have to do with solubility. I'm not going to read these all here, but you should know what a saturated and an unsaturated solution is. Just look at these definitions. A supersaturated solution. We go down towards the bottom here. Miscible and immiscible pertain to liquids. So if you mix together, say, water and alcohol, that would be miscible because they mix in together and you can't tell the difference. They're homogeneous. On the other hand, if you mix together, say, oil and water, obviously they're not going to mix together. You're going to have two different layers. That's said to be immiscible. So one of the factors affecting solubility is temperature. As this graph shows, the solubility of most solids increases as the temperature of the solvent increases. Take a look at sodium nitrate here. At 0 degrees Celsius, you can dissolve about 73 grams of sodium nitrate in 100 grams of water. Look what happens as you increase the temperature. If you get to about 80 degrees, you can dissolve about 145 grams. So clearly, as you increase the temperature of the solvent, you can dissolve more of the solute. Gases have the opposite effect. Look at these dashed lines. These are all gases here. Look at ammonia gas. As you increase the temperature, it becomes less soluble opposite effect. This is because the increase in kinetic energy causes more motion in the molecules in the solvent, which makes them easier to escape. Therefore, they're not as easily dissolved in the liquid. Let's take a look at another factor of solubility of gases in liquids. Here's an ordinary soda bottle. The pressure inside this bottle forces the gases to be dissolved inside the liquid. The more pressure there is, the more it forces the gas molecules to be dissolved. Once you release that pressure, there's nothing holding the gas molecules in, so they come fizzing out. We've all seen this happen before. We know that when there's no CO2 in the soda, it tastes flat, and that doesn't taste very good. So there's a calculation. It's called Henry's Law. As the pressure of the gas above the liquid increases, the solubility increases. So as I said, as you increase the pressure, the gas becomes more soluble. Solubility over pressure equals solubility over pressure. So let's do a Henry's Law calculation. Say we have some CO2 in water. The solubility is 1.45 grams per liter at a pressure of 100 kPa. kPa is a unit of pressure, much like pounds per square inch or millimeters of mercury. If you watch the Weather Channel, they usually talk about atmospheric pressure in millimeters of mercury, inches of water, torr. There's a lot of different units, but we're going to just use kPa for right now. So all we have to do is plug in numbers into this equation. These are pretty easy calculations, so let's take a look at this. Here's our formula. S over P equals S over P. So our solubility is 1.45 grams per liter at a pressure of 100 kPa. S over P equals, this is important, what is the solubility? X if the pressure increases to 200 kPa. All right, so notice this is an equal sign. This means it's crisscross math. We're going to do this. We're going to do this. This is different from multiplication. If this was times, we would multiply across. But this is equal, so this is where we crisscross. So we go 1.45 times 200 equals 100x. Okay. This comes out to 290 equals 100x. Divide by 100. Remember, you always divide by the number that's next to your x because you want to have the x be alone. So this comes out to 2.9, and the unit here is grams per liter. This is your answer. So this makes sense. These are proportional. If you have a solubility of about 1.5 grams at this pressure at 100, if you double the pressure, you would double the solubility. Makes total sense. So check your answers to make sure it makes sense. The solubility of methane gas in water is 0.026 grams per liter at 101 kPa. What is the solubility if the pressure was decreased to 75? So again, we're just plugging in numbers. Here's our first solubility, 0.026. That solubility is at 101 kPa. What is the solubility? We're solving for that solubility if the pressure is decreased to 75. So again, we're doing this, crisscross math, a little bit of algebra. So it's going to become 0.026 times 75 equals 101x. This becomes 1.95 equals 101x. Divide both sides by 101. So the answer is 0.0193 grams per liter. And again, that makes sense because if we started with 0.026, grams per liter at 101 kPa. If the pressure dropped, this number should get smaller, and it does. Let's take a look at another one here. The solubility of methane is 0.026 grams at 101 kPa. What is the new pressure if the solubility increased to 0.050? So same problem, just a little bit different. So again, let's just start off what we have here, 0.026 solubility over the pressure, 101 kPa. This time we're solving for the new pressure, which is on the bottom, if the solubility increases to 0.050. Same type of calculation, crisscross. We'll end up solving for x. So we have 0.026x equals 101 times 0.050. This becomes 5.05 0.026x. Divide both sides by the number next to your x. X equals, round it to 194. This is kPa because we're looking for pressure. And again, check to make sure it makes sense. If you had 0.026 at 101, look, the solubility almost doubled, you would expect your pressure to almost double also. That's our final answer.